Hello, algebra students. It's now time for lesson 5.5, comparing linear and nonlinear functions. So far this school year, you have seen tons and tons and tons of straight lines, but I have sad news. Not every graph is a straight line. And you've seen some of that with our introduction to absolute value functions. It was made up of straight lines, but not a perfectly straight line. So what I want you to be able to do today is I want you to be able to look at a table and tell me if it's linear or nonlinear, and how you know. And I want you to be able to look at a graph and tell me if it's linear or nonlinear. And of course, I want you to be able to look at an equation and tell me if it's linear or nonlinear. So a lot of this, again, this unit has been review, so check it out. Tables. Okay. The graph of a linear function shows a constant rate of change, or I like to call it a crock. Haha. A nonlinear function does not have a constant rate of change, so the graph's not a line. So if we're supposed to identify a linear function from a table, we just need to look for a crock, a constant rate of change. And that's what we're going to do. Just like the olden days, we're going to actually see if we can find the rate from each table, or the slope. So the question you have to answer is, does the table represent a linear or nonlinear function? And explain yourself. So in looking at that, I know that the slope, the rate, is the change in y divided by the change in x. So take a look at our y values here and what's going on with y every time. So I see that it's going from 40 to 32, and that would mean down by 8. 40 minus 32 is 8. And it's a negative change. Now I got that negative 8 because it's down by 8. You could also get that by taking y2 minus y1. 32 minus 40 is negative 8. Let's try that with this. If I take this y minus this y, 24 minus 32, yep, that's negative 8. 16 minus 24, that's also negative 8. Now remember, if it's a constant rate of change, it has to be the same every single time, and it's the change in y versus the change in x. So we have to figure out the x as well. Don't just look at that and say, yup. We have to make sure that our x values are doing the same kind of thing. So to get from 3 to 6, we're going up by 3, or 6 minus 3 is 3. From 6 to 9 is also up by 3. From 9 to 12 is also up by 3. So if I did my slope, the change in y over the change in x would be negative 8/3, and that happens every single time. So because it happens every single time, that's a crock. It's a constant rate of change. So yes, it's linear. That's how you would identify it from a table. Okay, the second table here, probably going to be a counter example if you know me well by now. Take a look. The change in y from 2 to 11. 11 minus 2 is 9, so that means this goes up by 9. Now when I'm going from 33 to 11, I'm thinking that's not 9, but 33 minus 11, yeah, that's up by 22. And 33 to 88, if you take y2 minus y1, 88 minus 33 is 55. Let's check the x just to be sure. 1 to 3, that's a change of up by 2. 3 to 5, up by 2. 5 to 7, up by 2. And I can see that the rate from here to here is 9/2. The rate from here to here is 22 over 2 and 55 over 2. So this would not be linear. So I'm going to write non-linear. And I'm going to write no crock, because I like writing the word crock. It makes me giggle. Alright, so from a table, if it's a constant rate of change, it's linear. If it's not, it's not. And don't worry, you'll be exposed to how to recognize other kinds of relationships from a table as well. I think my foot just hit the camera. Let me scooch it. There we go. So for now, you don't have to be able to tell me what kind of relationship that is, just that you know it's not linear. All right, moving along to the graphs. This is a tricky one. If the graph forms a straight line, it's linear. If it doesn't, it's not. So take a look at A. That's a straight line. Are you thinking, this is too easy? Yes, I know. So this is a straight line, so this would be yes. And I'm going to say it's because it's a straight line. Now for this second one, I'm hoping you recognize this as an absolute value. We just finished that section. And I know this is made up of straight lines, but it's not a single straight line. So this would be a no. It's not a single straight line. And C, yes, you are going to see graphs like this year. This is definitely not a straight line, so no, it's not straight. So that's how you can tell from looking at a graph. I know, pretty tricky. Look for straight lines and you'll know it's linear. Crazy, I know. Alright, turn your page. We're almost done. We just have to examine the equations now. Okay, so in a linear equation, there's a couple requirements. You've learned that there are several forms of y equals mx plus b, right? There's several forms of a linear equation. I mean, not just y equals mx plus b. So you have to be able to recognize it when it's in other forms as well. And here are kind of your top 3 things that you look for. If an equation is linear, x and y will both have exponents of 1. And you've learned that if it's an exponent of 1, we don't write the little 1. So you might look at it and say, well, x and y don't have an exponent. That's the same thing as them having exponents of 1. Also, x and y should not be multiplied together. So they need to be separate terms. You cannot have the x next to the y. That's not going to be linear. And last but not least, x and y do not appear in any denominators. Numerators are okay, denominators not so much. They're also not in as an exponent, like 2 to the x power. And they're also not underneath a radical sign, like the square root of y. So x and y aren't in any denominators, exponents, or radical signs. So I just have some linear examples and some nonlinear examples to kind of show you what these 3 things mean. So this is linear because x and y both have exponents of 1, x and y aren't being multiplied together, and x and y don't appear in any denominators, exponents, or radical signs. I know it's not y equals mx plus b, but I could arrange that into y equals mx plus b. With this second one, x and y have an exponent of 1. X and y aren't multiplied together. They're not next to one another. And I don't see x and y in any denominators, exponents, or radical signs. And same thing here. X and y both have exponents of 1. They're not next to one another. I don't see one in the denominator, exponent, or radical sign. So those are all examples of linear equations. Now take a look at this nonlinear. All right. So first off, it said x and y both have an exponent of 1. Well, I don't see any any exponents other than 1 here. So far it's okay. Number 2, or the second bullet, says that x and y aren't multiplied together. Do you see how x and y are multiplied together right there? That's what makes it not linear. So we can move on. All right, take a look at the second example. The first thing we look for, do x and y both have exponents of 1? Nope. This x has a cubed. It's not linear. And finally, when you look at the third example here, x and y both have exponents of 1. X and y aren't being multiplied together. But do you see how y is in the denominator spot? Yep, that means it is not linear. All right, you're all done.